So hi everyone, yeah, my name is Sheridan, and today I'm going to be talking about this idea of equifinality in Mechanistic. So what is equifinality? It's actually a really simple idea, just that an outcome can be reached through different processes. So I actually learned this idea really recently from my mom, who's a developmental psychologist, and she gave me the example of a kid who gets really good grades in school. So this is an outcome that can be explained through like a bunch of different processes, right? It might be that the kid is just really naturally gifted, or maybe he has a really strong mentor figure at home who makes sure that he always does his homework. But both of these processes could be reasons for why this kid gets good grades. But kind of the main idea is that in real life, a lot of the time it's not one or the other thing, but like both or multiple things all happening at the same time that are contributing to this end result. So if we port this idea into Mechanistic, we can say that a task can be implemented through different mechanisms. So there's a lot of places where this comes up in Mechanistic. One cool example is prior work in how LLMs do arithmetic, where people have found that models will actually sort of use a bunch of different heuristics that work really differently that all end up converging on sort of the same result. But what I'll talk about today is this task of in-context copying, which is just because it's something that I just worked on. So for in-context copying, we know for sure that definitely induction heads are responsible for this behavior, right? Like this is a really well-studied mechanism in models. But what I'll talk about today is that we actually recently found another mechanism that has the exact same outcome as induction heads, but gets there through a different reason. So the reason why we even looked at this in the first place is because we were studying previous token information in models, which is just the first half of induction circuits. So what we were doing is we just take a hidden state and try and train a probe to identify this previous token information in that hidden state. And we found that although these probes work pretty well for things like random strings of digits, as soon as we applied the same probe to naturalistic Wikipedia text, we saw this weird stripy pattern where actually not every token position was storing previous token information consistently. So what we wondered is maybe whether there was some other mechanism that was sort of responsible for filling in the gaps here and copying all these other positions. So we did a bunch of experiments and found that in addition to classic induction heads, there was also this other mechanism, which we called concept induction heads, that operates over multi-token units in sort of semantic chunks rather than individual tokens. So both of these mechanisms in this setting will increase the probability of the token card being next, but it's for totally different reasons. So for classic induction heads, this is because these heads are copying arbitrary sequences that have occurred in the prior context. But for concept induction heads, they're doing something kind of different, which actually doesn't require the tokens to be the exact same each time. So we find that like these concept induction heads, because they're copying sort of semantic units, are actually really important for things like translation, where you have like a word that's occurring multiple times in a context, but it's just sort of written in different tokens. So one example, like a qualitative example we have from our paper is this paraphrasing thing, where we're showing that both of these mechanisms are actually operating in parallel. So what we do here is we just take llama 3, copying the snippet of Python code, which it normally does perfectly. But if we ablate its token or classic induction heads, then what we see is that the model can actually still copy the snippet of code, but it just was only copying the semantics. So we see that it writes this code in list comprehension instead of writing it with the exact tokens that came before. And so we sort of interpret this as like the model still having this concept induction capability that's still operating totally independently of the token induction heads that are also there. So our paper called the Dual-Route Model of Induction goes over this in way more detail, and we get a lot of cool stuff from this. Like for example, we can get like language independent word representations that are really helpful for translation. Or what the poster that I was just presenting here is, we get some cleaner word-to-vec style analogies if you just focus on like the concept subspace that these sort of semantic heads are reading from. But the main thing is if we had stopped at classic induction heads as an explanation here, we never would have found all this cool semantic material inside models. So my main takeaway again for today is just this idea of equifinality, that a task can be implemented through different mechanisms. And actually, as soon as I say it like this seems kind of obvious, right? Like the whole point of Mechanistic is we have some outcome and we're just trying to figure out like what is the mechanism that contributed to this outcome. But I guess my main takeaway here is just that a lot of the time it's not like one or the other thing, but there can be tons of things all happening at once that all contribute to this little monkey getting good grades. So thank you so much.